So in this next video, in the higher level AI mathematics YouTube series that I'm running, we're going to be looking at Markov chains. Now, if you haven't done already, watch the video on matrix transformations to start with. This lesson leads on from that. Now, a Markov chain is a series of matrices that represent some form of movement. We know that graph transformations can be represented by matrices. Matrices represent some form of movement. A Markov chain is a system of matrices in which we calculate the probability of each event, and it's dependent only on the state of the previous event. So, for example, if it's raining or it's dry one day, what's the probability of it being wet or dry the next day? We use it to calculate probabilities at different time intervals, so 1 day, 5 days, 100 days, and we use it with an initial state matrix, S0, and a transition matrix, T. A way of summarizing transition matrices is with something like a transition state diagram. So in this question here, we've got a day or a couple of days where initially it might be wet or dry, that's the W and the D, and then it shows you how it changes from day to day. So this probability here, the 0.5, is the probability of it being dry given it was wet the day before. The probability that it's dry given it was dry is this one here, 0.6. That's like it's dry one day and it stays dry the next day. Now the transition matrix that's associated with this diagram will look like this. It's really important you note that the columns sum up to 1, and it's from and to. So this number here, 0.4, is this number here, and it's saying that it is dry today. The probability of it raining or being wet tomorrow is 0.4. And you can see that's with this arrow going along. So we can write it as a diagram, or we can write it as a matrix. The matrix is much nicer and it's much easier. Once you've done a few and you've got used to them, it makes a lot more sense. Now, a transition matrix is a square matrix which summarizes the transition state diagram. It's really important that it's square, and it's obvious it's square because it's from and to, and the systems must be the same. What's super important is you remember that the sum of each of the columns is 1. If it's not 1, then it won't work when you're starting to multiply out the matrices together. The transition matrix is very useful if there are more than 2 states in the system and you want to know after like 5 days or 10 days or 15 days. So here's a question. In Saigon, if it rains one day, the probability that it rains the next is 0.9. If it's dry, the probability that it will be dry the next day is 0.6. Now, the associated transition matrix, remember, we'll start with dry, and then we'll go wet, or rain, dry, and wet. Now, if it's dry one day, the probability it's dry the next is 0.6, so that goes here. Remember, it's from and then to, so I have from here, and then to here. We know the probabilities sum up to 1, so therefore this must be 0.4. If it rains one day and rains the next, that's 0.9, and therefore this one must be 0.1. That shows you that the columns must sum to 1. So we'll say the transition matrix is 0.6, 0.1, 0.4, 0.9. Now let's say I wanted to know the probability after like 5 days, what it's going to look like. What we'll do is we'll raise the transition matrix to the power 5. Now understanding what these entries mean is super important. This means this number here, this is in the dry to the dry column. This probability is if it's dry today, in 5 days' time, the probability that it will be dry is 0.225. It's basically like doing a tree diagram with 5 branches and then working out all the different combinations of starting at dry and ending at dry. This one down here, the 0.806, is the same. It's just wet to wet. So if it's raining today, in 5 days' time, the probability of it raining is 0.86. Let's now jump over to a different kind of style of question. A mouse is moving around a maze, and the maze looks like this. Part A is to write down a transition matrix that represents this. What's important to note is that the mouse must move every day. So once a day, the mouse must move. So if he's in A, he must move. He can't stay in A. So if we think about the transition matrix, right, it's A, B, C, D going to A, B, C, D. We know if he's in the diagonals down here, it's 0, because if he's in D, he must move. If he's in C, he must move. If we think about where A, if he's in A, where can he go? He can go here, here, or here, and those are all the doors, and we assume that the probabilities are the same. There's therefore 1/3 chance of going from A to B, and there's 2/3 chance of going A to C, and there's no chance of going A to D. Similarly, if we start in B, he can go to A, C, or D with equal probabilities. There's 1/3, 1/3, and 1/3. If he's in C, he can go to A with 2 doors. He can go to B with 1 door, but he can't go to D. So therefore, it's 2/3 to A, 1/3 to B, and no going to D. If he's in D, he can only go to B. So therefore, it's 0, 1, 0. We note that the columns sum to 1. Super important. Let's say part B is to work out, let's say so the mouse starts in C. Oops. Let's say we want to know after 5 days, we want to know the probability that he's in A. So what I'm going to do is I'm going to take my transition matrix, we'll call this T. I'm going to raise it to the power 5 to start with. After raising to the power 5, this is the matrix that I get. The columns should add up to 1. They may not exactly because I've rounded the numbers. If you give them to the exact, like 10 digits, 11 digits, whatever, then that will add up to 1. Because I've rounded it, might not add up exactly. We start in C, so that means we start here. After 5 days, what's the probability of being in A? So that's from C to A. So that's this probability here. The answer is 0.36. I hope that's been helpful. The next video will be on steady state matrices, which follows on from this lesson.